Today we'll be talking about the number of ways you can select k objects from n distinguishable objects without replacement or order does not matter. To clarify, our sampling problem will have a collection of objects. There will be n of them. They will be distinguishable. We will select k of them. When we select each one, we will not put it back into the sampling pool to be able to be chosen again. And the order of the final sample will not matter. The short answer to the number of ways we can do this is n factorial divided by n minus k factorial times k factorial. The reason why this is a tricky result to get to, is because of the fact that order does not matter. Because ordering does not matter, we have to consider the cases that we may be overcounting and account for them. To get to the number of ways we can sample under these specified conditions, we can think of a similar sampling problem and sort of tweak the answer. First, let's think of the ways we can select k items from n distinguishable items with replacement or ordering does matter. We can find that answer and then divide by the appropriate quantity that we need to stop counting repeats. Repeats meaning results that are reorderings of the same set, samples that are reorderings of the same set. To illustrate this, take, for example, a situation where we are selecting from 3 items, A, B, and C, and we are selecting from 2 items. Let's look at the first result, A, B. Here, A, B. We have this result, and if ordering did matter, then we could have this result too, BA. But because we're considering the case where ordering does not matter, we only want to count one of these, so we get rid of one of them. And we do that for any possible repeat outcome. So in the case where ordering does not matter, we would instead have this result rather than this resultant list of possible samples. So for every sample in the set of possibilities, the number of repeats you have is predictable. And this is because for every sample in the set of possibilities, every possible permutation of that set is in the set of possibilities. As we just showed, A, B, in the set of possibilities, A, B is in there in itself, and a permutation of A, B is also in there, BA. And the same can be said for AC. AC is in the set of possibilities, but so is CA, a permutation. BC, there is BC, and there's also CB in the set of possibilities. So because for every possible sampling outcome, there is every permutation of that sampling outcome also present in the set when we're sampling in the situation with order mattering. What we can simply do is divide by the number of ways you can rearrange any given sample outcome to get rid of that overcounting. So we divide by the number of permutations there are for each set to avoid counting identical sets. And this number is k factorial. This is why the number of ways you can choose k items from n distinguishable items without replacement or ordering does not matter is npk divided by k factorial, or n factorial divided by n minus k factorial divided by k factorial. Some interesting things that this statement tells us is that if we look here, the number of ways we can choose k items from n items without replacement without order mattering is exactly equal to the number of ways we can choose k items from n items without replacement with order mattering divided by the number of ways we can rearrange the sampled items. So they're exactly equal, just divided by the number of ways you can rearrange the sampled items. What this also tells us is that the number of ways we can do the sampling without order mattering is always less than or equal to the number of ways you can do it with order mattering. This sampling method is applicable to real-world situations. For instance, let's take the case where we have 12 employees in an office, 5 positions on a board are open, and they're only hiring from within, so you can only choose from the employees in the office. We want to know how many possible outcomes are there for this hiring process. Well, we can model it with our sampling method. And this is because we're selecting a finite number from a finite pool. The elements of the pool are distinguishable because they're all just people and people are distinguishable. There's no replacement because no one person can fill multiple roles. So we don't want to put them back once we've chosen them for a role. And the order does not matter because the 5 positions are identical. Because we can model it with our sampling method, we can just plug in for the answer. N is equal to 12 because we're selecting from 12 employees, and K is equal to 5 because we're selecting 5, we're filling 5 slots. So when we plug it in, we get 792. So there are 792 total outcomes for this hiring process.